This section explains the Group Relative Policy Optimization GRPO model and code implementation. Let's first look at the GRPO model overview. GRPO is a variant of policy gradient methods used in reinforcement learning. It improves the stability and efficiency of policy updates by grouping trajectories based on their performance and updating the policy in a way that emphasizes relative performance across groups. The key insight behind GRPO is to focus on the relative performance of different groups of trajectories, rather than treating all trajectories equally. This method can lead to more stable and efficient training in complex environments. Policy gradient methods. In reinforcement learning, the goal of a policy gradient method is to optimize a policy πθ parameterized by theta, which maps states S to actions A. The objective is to maximize the expected return from following the policy. The policy is updated using gradients derived from the total expected reward. The core idea behind policy gradient methods is to use the advantage function, which estimates how much better or worse an action taken at time step t is compared to the average action at that state. The objective function for policy optimization is usually defined as follows. GRPO algorithm. In GRPO, the key idea is to group trajectories based on their return and perform a relative update of the policy for each group of trajectories. The groups are weighted according to their performance, with higher performing groups having a greater impact on the policy update. Steps of the GRPO algorithm. 1. Collect trajectories. Run the policy in the environment to collect a set of trajectories. Each trajectory consists of state-action pairs, along with their rewards and action probabilities. 2. Group trajectories. Sort the collected trajectories by their total return and group them into several subgroups. The number of groups is defined by the hyperparameter ngroups. 3. Update policy. For each group, update the policy based on the performance of that group relative to others. This ensures that better performing groups have more influence on the policy update. 4. Update value function. Update the value network using the standard mean squared error loss between the predicted values and the returns from the trajectories. Formula derivation. The policy update rule in GRPO is based on a surrogate loss function with a clipping mechanism. The key idea is to use the ratio of the current and old policy probabilities, often called the importance ratio, to compute a trust region in which updates are considered safe. Clipped surrogate loss. In the standard policy gradient, the update can be unstable due to large updates. To stabilize the updates, we use the clipped objective function introduced in proximal policy optimization, PPO, which restricts the ratio of new and old policy probabilities within a certain range. The ratio is defined as follows. The clipped objective function is as follows, where epsilon is a small parameter that controls the clipping range, typically 0.1 or 0.2. Group relative loss. In GRPO, we extend this by incorporating the group relative aspect. Instead of treating all trajectories equally, we weight the loss by the performance group. Let the group performance GI for group I be proportional to its return. The relative weight of group I is as follows, where I is the index of the group, from best to worst, and n groups is the total number of groups. Thus, the final policy update loss becomes as follows, where AI is the advantage of action A at state S, GI is the performance weight for the group containing the trajectory. Epsilon is a small parameter controlling the range of safe updates. This loss function is applied separately to each group of trajectories, ensuring that higher performing groups have a greater influence on the policy update. Policy update process. The policy update proceeds as follows. 1. Calculate advantage. For each trajectory, compute the advantage as the difference between the return and the value function. 2. Compute importance ratios. Calculate the ratio for each action taken, which measures the change in policy from the old policy to the new policy. 3. Calculate surrogate loss. For each trajectory group, calculate the surrogate loss using the clipped objective function, weighted by the group's performance. 4. Backpropagate loss. compute the gradient of the loss with respect to the policy parameters, and update the policy using backpropagation. Now we implement the GRPO code. Policy network class. Trajectory class. GRPO class. Test case for cart pole environment. Test case for Acrobot environment.